Good day. In this podcast, we are going to interpret and analyze motion graphs. In particular, we're going to be looking at speed graphs and acceleration graphs. Getting started. First thing I do when I look at a graph is look at its title. What is it telling me? So this is a speed graph. Next thing I would do is look on my axes to see how they're defined. So on my horizontal or x-axis, I have time. So T for time, and the unit of time here in parentheses will be seconds. So time is on my horizontal or x-axis. On my vertical or y-axis, I have distance. 10, 20, 30. What unit is this? We'll say meters. So a distance on my vertical y-axis. Now, I have two lines. I have a green line and a purple line. And the slope of that line happens to be the speed. So let's, for the sake of the graph, give you an example. Let's say this is a cross-country meet. So I have a green team and a purple team. So these are two different runners, and we're going to analyze and interpret their speeds at different times. So for the green team, let me get my green pen, and we'll start analyzing their speed. And let me pose a question to you to begin with. If we're starting at a starting line, they're both taking off from 0. Who do you think is traveling faster in the first 2 seconds? The green runner or the purple runner? Well, let's do some math and find out. So speed, first thing I would do is, that's what I wanted to know, is how fast are they traveling to begin with. So I'm solving for speed. So speed equals distance divided by time. And this graph is not exactly precise, but roughly in the first 2 seconds, I want to know how fast they're traveling. So the first 2 seconds, the green runner went about 30 meters. So what is their speed? Their speed is 15 meters per second. That's exactly how I would do my work, show my work, and I would, again, circle my answer. Now, let's change to the purple pen and see what's going on with our purple runner. What is their speed? And we've got 3 different things happening during the course of the race for the purple runner. So at the 3 different points on the line, we'll calculate the 3 different speeds. So the speed at point 1, what is it? Well, we're going to plug in our distance and our time. Again, it's 2 seconds. And in 2 seconds, they went approximately, again, we get to be approximate here, 20 meters per second, or for 2 seconds. Therefore, their speed is 10 meters per second. So if you guessed, and again, either circle or box your answer for me. If you guessed that the green runner was traveling faster, you were right. You were right, and here's the math to back it up. Now let's figure out what is happening to the purple runner from the 2nd to 3rd second. So let's just plug in our change in distance, our change in time to find out. So I'm going to start with time. So from the 3rd second to the 2nd second, which is a change of 1 second, what did they do for their distance? Well, they started at 20 meters. This is my change, so I'm subtracting it. And they ended at 20 meters. So they went 0 meters in 1 second, which means 0 divided by 1 is 0 meters per second. So therefore, their speed is 0 meters per second. They stopped. That's what happened at point 2 in their race. They stopped for 1 second, maybe to catch their breath, maybe they quickly took a drink of water, something, but they stopped. Now let's see what's happening at line 3. Again, it's my change in distance divided by my change in time. So my change in distance, for some reason, I like to start with time. So they ended at 5 seconds, and 3 seconds, and now I'll plug in my distance. They ended, again, this is my final distance minus my initial distance. They started again at 20 meters. So that's a negative 20 meters over 2 seconds. So they went a negative 10 meters per second. Same speed as when they started out the race from line 1, same speed, 10 meters per second, but here it's a negative speed here. And what this means with distance, a negative distance means they changed direction. So they went back to where they started for some reason, which we don't hardly ever see. They went back to the starting line. They changed their direction because their speed is still 10 meters per second, but they changed their direction. Okay, so that is our speed graph. Now we will move on to acceleration. If I can get, sorry. Come on. Okay, acceleration. Actually, we're now going to define acceleration. Acceleration is the change in speed or direction, which is velocity over time. So again, acceleration is the change in velocity divided by the time. When I think of something accelerating, I often think of a race car, a plane, a roller coaster, starting at 0 and taking off super fast. That's what I think of as acceleration. Well, that's a positive change in speed. But that's not always acceleration, because acceleration is a change in velocity over time. So remember, velocity has 2 components, speed and direction. So I can actually be accelerating with a constant speed, but I'm changing direction. For example, if I think of a merry-go-round or something that goes in a circle, like a carousel, those horses on a carousel, they're going at a constant speed if you're riding on that horse on a carousel, but they're going in a circle, which is always changing direction. Therefore, a horse on a carousel is always accelerating. Even though it's going the same speed, it's always changing its direction. All right, okay, so again, that was my, there's the equation for acceleration, which the average, to find the average acceleration of something, I take the final velocity. Again, this is where my change in velocities minus my initial change. And this is what I was doing kind of on the speed graphs. Minus my final time, subtracting my initial time from my final time. Okay, so let's now look at an acceleration graph. So the first thing, let's back up to that. What's my title? Graphing acceleration. That's what I'm looking at. Now I'm going to look at my axes. So on my horizontal or x-axis, same as a speed graph, I have time. And we're going to put this in seconds again. The unit is seconds. So again, on my x horizontal axis, I have time. This, for an acceleration graph on my y or vertical axis, this time instead of being distance, it's actually speed. And my unit for speed is going to be meters per second in this example. Okay? So let's say an object accelerates at 1 meter per second squared. That means the velocity of the object increases by 1 meter per second each second. So if the object was initially at rest, its velocity would be 1 meter per second after 1 second, 2 meters per second after 2 seconds, and so on. Okay, let's see what's going on with the slope of this line and calculate the acceleration at the different points on this graph. So, I'm going to change my pen again, just to be consistent to red. So at A1, what's the acceleration? It's starting at rest. It's starting at 0. And I'm going to plug in my numbers here. So velocity, V and S, you can kind of think of as interchangeable variables. Velocity, again, is speed and direction, but if no direction is given, just use the speed. So my final speed, well, I'm trying to calculate again the slope of line 1. So let me, again, I'm in the habit of starting with time. So 2 seconds minus, I started at 0 seconds. At 2 seconds, it had was traveling at 30 meters per second. Again, its initial velocity was 0. So that turns out to be 30 divided by 2, or again 15 meters, this time per second squared. 15 meters per second per second. That's the acceleration at line 1. The acceleration at line 2, I went from 3 seconds to 2 seconds, and I went from 30 meters to 30 meters, which is 0 meters over 1 second. Oops. And that's, again, speed, meters per second. I'm writing on top of myself. I apologize. Anyways, I didn't have my units right here. 0 meters per second. Okay, let's now calculate the acceleration at line 2 on the graph. So putting in my change in time. Oh, it's 4 seconds minus, that's the final time, minus the initial time was 2 seconds, where it started from at A2. And its speed now. Its final speed is 30 meters per second. And its initial speed was 30 meters per second. So I have 0 meters per second over 2 seconds. That is 0 meters per second squared. So 0 meters per second squared, here it doesn't mean that it has stopped traveling. What it means is it's stopped accelerating. There's no change in its speed, is there? So this is actually cruise control. This is a constant speed, 30 meters per second. Constant speed, cruise control, they're not accelerating. A3, let's see what happens here. So my final time, it was 5 seconds. Started at 4 seconds. And my change in speed is, well, I finish at 0 meters per second, and I started at 30 meters per second. So I have a negative 30 divided by 1. Negative 30 divided by 1 is a negative 30 meters per second squared. A negative 30 meters per second squared. So that line is steeper. And what this means is they are slowing down to a stop. So it's a negative acceleration. A negative acceleration we could also refer to as deceleration. So they put the brakes on and came to a quick stop. So to give you an example of what's happening at this line, I think of a plane. Although the time is not right, a plane wouldn't do this in 5 seconds. But again, a plane is going to take off from a 0 speed and accelerate, have a positive acceleration. Once they reach their cruising altitude, they put cruise control on. So at line 2, put cruise control on. They have a constant speed, so they're not accelerating if they're going in the same direction. And then once they've gotten to their destination, they put the brakes on and have a negative acceleration or deceleration and quickly come to a stop. So that is an example of what is happening in those graphs. So, we will now summarize what we talked about. We talked about graphing speed, and with graphing speed, again, the slope of the line is the speed, because on the horizontal x-axis I have time, and on the vertical y-axis I have distance. I find my distance divided by time, and I get my slope of the line for speed. We also looked at acceleration graphs. Acceleration is the change in velocity divided by time. A change in velocity occurs when an object changes either its speed or its direction. We can calculate the average acceleration of an object by taking the final velocity minus the initial velocity and dividing it by the final time minus the initial time. So our change in velocity over change in time gives us our average acceleration. When an object moving in a straight line speeds up, its acceleration is positive. When its line is flat, it means it's not accelerating, or it's on cruise control, constant speed. And when an object is moving in a straight line, if it slows down, its acceleration is negative. We also referred to that as deceleration. Next up, in our next podcast, we will look at motion and forces.